I also had a few requests to go over some problems from the test practice that I posted. So the first one that was requested was number 3, which of the following is occurring at the anode in an electrochemical cell? So the definition of the anode is where oxidation happens. So that knocks out C and D, where it's saying a substance is reduced. And the definition of oxidation is that electrons are lost. So a substance is oxidized when it loses electrons at the anode. If you're having trouble remembering which one's which for anode versus cathode and oxidation versus reduction being gained and lost, there are some mnemonics that can help. So for anode versus cathode, this is really kind of a weird one, but if you remember the phrase anox, phrases, I guess, and red cat, for anode is oxidation, and cathode is reduction, or reduction is cathode. If you try to like flip these phrases around, it doesn't really work. Like anox and red cat are grammatical phrases that make sense. Red, what would it be? Red and ox cat like don't go together the way they should. If you're more of a visual person, the image of like a red cat riding on an ox might be helpful, but that's the one that people usually teach. For loss and gain of electrons, there are a few different popular mnemonics. Oil rig is probably the most common one for oxidation is loss of electrons, reduction is gain of electrons. My personal favorite is Leo the Lion says grr. That's the one I was taught, and it's cuter, so I like it. But they amount to the same thing. Loss of electrons is oxidation. Gain of electrons is reduction. I also like the Leo says grr mnemonic better because it focuses on the electrons, that the electrons are actually part of the phrase. Oil rig tends to get phrased as oxidation is loss, reduction is gain, and it's like, well, loss and gain of what? And that's a really critical part of understanding what oxidation and reduction are, but whichever one of these works for you is fine. So anyhow, oxidation is loss, reduction is gain of electrons. Oxidation occurs at the anode. Reduction occurs at the cathode, always. So the next one that was requested was number 7, based on your reference information. So that means your standard reduction potentials. Which of the following half cells should you pair together to create a galvanic cell that produces the greatest voltage? So the greatest voltage is going to be produced by the most favored reduction and the most favored oxidation occurring together. So the most favored reduction is going to be the highest reduction potential. So we want most favored reduction and most favored oxidation occurring together. So our most favored reduction is going to be the one with the highest standard reduction potential, which is option B here. So that guy is definitely going to be involved as the cathode reaction, as the reduction half reaction that is part of the galvanic cell we're trying to produce. And then our most favored oxidation, since oxidation and reduction are opposite processes, our most favored oxidation is going to be our least favored reduction, which means our lowest standard reduction potential, because when we change the sign, that is going to become our highest standard oxidation potential. So that going in the oxidation direction will be our most favored oxidation process. So to get the highest possible voltage, looking at just your standard reduction potentials, you always want to pair the very highest one with the very lowest one that you have available to you. Because when you flip the sign on that low one, it now becomes the highest oxidation. And then you add those two things together to get your cell voltage. So biggest difference in reduction potentials is going to get you the biggest cell potential overall. And then the last request was number 10. I'm just going to go through part A. There were a few parts to this one, but they're all fundamentally the same. They're all asking you to do the same thing, so it's the same process. So you're given line notation for a galvanic cell here, and first asked to write the net reaction occurring in that cell. So to do that, we need to remember that everything before that double vertical line here is part of our anode, and everything after that is part of our cathode. So we can write the anode and cathode half reactions based on our line notation here, knowing that reactants are always listed first, products are always listed second. So our anode reaction is aluminum becoming aluminum 3+. To balance that for charge, we need to add 3 electrons to the right. So when you're writing half reactions, make sure that you balance them. We put our thing that is being oxidized and what it turns into, but this isn't a balanced reaction as it's written. It's not balanced for charge, so we need to include electrons. And then our cathode reaction is lead 2+ becoming lead. And to balance that, we need 2 electrons on the left. So in order to add these back together into our net reaction, we need to equalize our numbers of electrons, which means we're going to need to multiply our first half reaction by 2 so that we get 6 electrons here, and our second half reaction by 3 so we get 6 electrons there as well, so that those will cancel out in our net reaction. So when we do that and we add them together, we're going to have 2 aluminum on the left and 3 lead 2+ on the left. And then on the right, we'll have 2 aluminum 3+ and 3 lead. And that is our balanced net reaction that is occurring in this cell. So the next part asks us to calculate the standard cell potential. Remember that little degree sign, that little naught symbol, means standard. So all we're doing here to calculate our standard cell potential is finding our standard reduction potential for our reduction and adding the standard oxidation potential for our oxidation. So if we consult our list of standard reduction potentials, we can find those things. Our standard oxidation potential for aluminum to aluminum 3+ is 1.66 volts. Our standard reduction potential for lead 2 to lead 0 is negative 0.13. So we'll have negative 0.13 plus 1.66 which gets us a standard cell voltage of 1.53 volts. And then the last portion is asking us for this cell to compare the non-standard cell potential to the standard cell potential. So what we just calculated was the standard cell potential, which means when all of our concentrations are 1 molar, that is our voltage. But the concentrations given in our line notation are not 1 molar. So this is not a standard cell, which means that we need to figure out if we are closer to equilibrium than a standard cell, which would mean that our cell potential is less than standard, or if we are greater, if we are farther away from equilibrium than a standard cell, our potential would be greater. So we do that by calculating Q. For a standard cell, our reaction quotient is equal to 1 because all of our concentrations are 1. And Q is just the value of the equilibrium expression with all of your concentrations plugged in. So no matter what your equilibrium expression looks like, Q is always 1 for a standard cell, and then K is always a very big number. So as Q gets larger, we're getting closer to equilibrium. As Q gets smaller than 1, we're getting farther away from equilibrium. So we need to write our equilibrium expression. So on the product side, we have aqueous aluminum ions. Lead is a solid, so that's going to get ignored. So we have Al3 plus, coefficient of 2 becomes an exponent of 2. On the reactant side, aluminum is solid, so that gets left out. Lead is aqueous, so that we include. Coefficient of 3 becomes exponent of 3. So we have the concentration of aluminum 3 plus squared on the top, concentration of lead 2 plus cubed on the bottom. And both of these concentrations were given as 0.5. So we have 0.5 squared over 0.5 cubed, which is the same as 1 over 0.5, which is equal to 2. So what this is telling us is that Q is larger than it is in a standard cell. So that means that we are closer to equilibrium than a standard cell, which means our cell potential is smaller. Our cell potential is measuring how far does this reaction have to go to get to equilibrium. So standard is comparing Q equals 1 to equilibrium. As Q gets larger, we're getting closer to equilibrium. So our distance that we need to go has gotten smaller, which means our cell potential has gotten smaller as well.